This is chapter 6.2, part 1 lecture. This section is again going to be talking about discrete probability distributions, but this time we'll be talking about something called the binomial probability distribution. And so what we need to recall that in section 6.1, the previous one, we stated that a probability distribution could be presented using tables, graphs, or mathematical formulas. So in this section, which involves the binomial probability distribution, we'll be using a formula to generate answers, and specifically, we'll plug values into StatCrunch that use the formula. And a binomial probability distribution involves situations where there are only two outcomes, and many times we refer to those outcomes as success or failure, depending upon what we define as success, the thing we're looking for. And experiments in this case are called binomial experiments because, again, binomial two outcomes. And so let's go ahead and take a look at our note sheets. You have your 6.2 note sheets out. Looking at the first part here, we have some examples here to look at. So example 1, identify binomial probability distributions. Determine which of the following probability experiments qualify as a binomial experiment. For those that are binomial experiments, identify the number of trials, probability of success, failure, and the possible values of the random variable x. And so in this case, before we can do that, we need to know what is a binomial probability experiment. And so we here have in your note sheet a place to mark that down. An experiment is said to be a binomial probability experiment if the experiment is performed a fixed number of times. That means a finite number of times. Each repetition of the experiment is called a trial. We've used these terms before, called a trial. That's the first situation. The trials are independent, and that refers back to chapter 5. The outcomes are independent. This means that the outcome of one trial will not affect the outcome of another trial. For each trial, there are two what we call mutually exclusive. There are two mutually exclusive, or what we called in the past, disjoint outcomes. Success or failure is the common phrase we use for that. And then we know that the probability of success is fixed, does not change, it's fixed for each trial of the experiment. So once we have that situation, these are the criteria, we can go ahead and then determine if these are binomial experiments. Part A, an experiment in which a basketball player has historically makes 80% of the free throws, is asked to shoot 3 free throws, and the number of free throws made is recorded. So think about it. Is that a binomial probability experiment? So after thinking about it, what do you think? We would say yes, that this is a binomial experiment. In this case, the number of trials is 3. They're asked to shoot 3 free throws. The probability of success, which we call P, is 0.80. The probability of failure, which we call Q, is 0.20. And the possible values for X are 0, 1, 2, or 3 successes, which is making them. Part B, according to the Harris poll, 28% of Americans state that their chocolate is their favorite ice cream. Suppose a simple random sample size 10 is obtained, and the number of Americans who choose chocolate as their favorite ice cream is recorded. Is this a binomial probability experiment? Consider your criteria. We're going to be asking 10 people. And so that would be 10 trials. Whether they like chocolate or not, we're going to assume is independent of each other. And then we only have 2 outcomes. Either they like chocolate or don't like chocolate. And the probability of success is 28%. So in this case, we would say, yes, this is a probability experiment. N is 10. The probability that they like chocolate is 0.28. The probability of failure that they do not like chocolate is 0.72. And the possible outcomes for this are yeah, either they do, it's going to be from 0, 1, all the way up to 10 people may say they like chocolate as their favorite ice cream. Part C, is this a probability distribution? 3 cards are drawn from a deck without replacement, and the number of aces is recorded. Consider that. So you're thinking about it. And in this case, it almost sounds like it's going to be a binomial experiment because we have outcome, either it's an ace or it's not. The probability here, the problem here with this one is that this is not. This is no, not. And the reason is the probability of success, the probability, what does P equal to? Well, in one case, it's, for the first card, it's 4 out of 52. And then after that, the probabilities change. And so let me make a note of that. Probability of success changes because once you pull one card without replacement, it changes the probability. Probability of success, right? Probability of success changes. We could say it is not fixed. That's why the answer is no. It is not fixed. And so that's why here, because it will change. You have 53 cards, 51 cards, so the probabilities will end up changing. And so that's our introduction to probability, binomial probability experiments.